In 3.2, we are getting into the least squares regression, and we'll look deeper as to what that exactly means, but we're going to focus in the beginning on just the term regression line, and it summarizes the relationship between two variables. Regression, unlike correlation, because correlation didn't really care what our x and what our y was. It was just how close are our values to that regression line. It does require that we have an explanatory and a response variable, because we're going to get into linear relationships, and linear relationships require a slope. So our slope will be dependent on which our explanatory and response variables are. A regression line is a line that describes how a response variable y changes and as an explanatory variable x changes. We often use a regression line to predict the value of y for a given x. So you want to think about function relationships. As x goes in, what happens to y? So we're going to go back to our data for that little panda, Taishan. Been meaning to look it up. Somebody look up Taishan, find out where he is now. Hopefully he's still around with us. We can see now that our scatter plot has added a regression line to it. So it's this scatter plot that we saw in the last lesson. And we can now see we've added on, and we actually did this together in class. We worked through how to calculate this correlation. Let's review the last lesson. We're going to describe this scatter plot. There is a strong, so remember you need these three parts: the strength, the direction, and the form. In most cases, it will be a linear form. There's a strong positive linear association between Taishan's age in days and weight in pounds. We can now say this with a bit more confidence because we actually do know that the R value is strong. But let's not forget this possible, sorry, we didn't do any calculations, it's possible outlier. And just so you know, you'll never actually have to calculate an outlier. You just need to mention it if you see one. Let's add to our description, there's a possible outlier at 158 days. So what I did, just look at the graph and then looked at my actual data, went back here. I could see that that happened around just above 35 pounds. So right about here. So that had to be the 158 days. We're going to use some formulas and terminology for describing the regression line. Just remember that your y variable is your response variable, your x is your explanatory. So just remember that x-axis, explanatory. That's an easier way to keep those two memorized and differentiated. So our regression line formula is known as this y hat. Okay, so we really read that as y hat because it's got a little hat on it, equals a plus bx. You might be more familiar with this formula if I rewrote it as y equals mx plus b, the slope-intercept form of a line. In statistics, we just write it slightly different. We put our y-intercept first, and we call it the letter A. Our b is the slope, and y hat is actually how we read this. So let's just look at how these two equations are connected. Y hat is the predicted value of the response variable for a given value of the explanatory variable. So what we're saying is we can predict using our regression line what a value of y might be, even if it's not part of our scatter plot. In our slope-intercept form, this would be equivalent to just the letter y. That's pretty obvious. B is the rate of change. So this is where things can get a little confusing because in our slope-intercept formula, it's usually M. So in statistics, you need to realize that the letter B is what we use to represent our slope. A is the initial value, or what we call the y-intercept. It's the predicted value of y when x equals 0. This is the letter that would be equivalent to our B in our y equals mx plus b. So now it's the letter A. It really honestly doesn't matter whether you remember the correct letters for this. What is important is that you remember the order that these come in. You're going to see that initial value first. Okay, so you're going to see that A first, and then you're going to see the slope times your explanatory variable. Let's take a look at an example, and I think it's going to help you understand the connections here. First off, would you do me a favor, and we're actually going to put a hat on that word weight. Right here, it should have had this little peak on it. This should have been weight hat, our predicted value. So you'll sometimes see a whole word printed out like that with a hat on it. If I make my connections to my formula up above, we can see we've got y hat equals a plus bx. So we can see which part is which. If I'm looking for my slope, that is going to be my b, which is my 0.127. It also tells me right here that this is age in days, so I need to include that context in my interpretation right here. So I've described it, slope. I put a note that it's also sometimes asked for the rate of change. Just realize those could be worded either way. Taishan increases 0.127 pounds for each single unit of day he ages. The y-intercept is now our A, or also known as our initial value, and that's going to be our 13.7. So once again, y-intercept, describe it as at birth or 0 days of age. Taishan's predicted weight is 13.7 pounds. So notice I said predicted weight because 0 days of age was not included in our original data set. Also, I forgot to mention when I talked about slope, I did say increases. Now, if this had been a negative number, we could have just said decreases here. So you don't want to say increases by a negative number. That wouldn't make sense. So you'd say it decreases by whatever amount if your slope is negative. Let's go ahead and look at an example of how we would use a regression line to make predictions. So it's really just plugging numbers in and solving. So how much would you predict Taishan to weigh at 210 days? So after I plug 210 in for my explanatory value, I get 40.41 pounds. So don't forget that unit whenever you give your answer. I'd like you guys to go ahead and try this next problem for 348 days. Go ahead and predict Taishan's weight. So if done correctly, your predicted value should be 57.896 pounds. And finally, at 3 years, since our original unit was days, we are going to multiply that by 365. So whenever it asks you to convert years to days, you can always just use 365. That's a unit you're expected to know. You don't have to worry about leap years. That ends up being 1,095 days. So that ends up being a whopping 152.765 pounds after 3 years. So it would be interesting to look up Taishan's actual weight at 3 years. I bet it's actually recorded somewhere, and see how close our prediction is. And that concept actually takes us to this next idea of extrapolation. Extrapolation is the idea that we're trying to make a prediction that's far outside of our original data set. So 3 years, that 1,095 days, was way far beyond our original data. If you go back to the first day page, you can actually see that our largest day on our table is only 249 days. So 1,000 and beyond is way outside of that area. So when we're talking about this, and often even 0 is an extrapolation, we rarely have in our data set our initial value of for 0 amount of whatever our explanatory variable is. And so that's why sometimes you'll see a y-intercept that's negative and it doesn't make sense in your problem, like a negative weight for our panda could have happened. In our previous example, of course, that 3 years would be our extrapolation. This feels like a good place to stop and break for the next video.